for another minute and then. All right, let's get started. Hello, everyone. Thanks for coming the 11th spotlight session of our RMP conference. So we are very delighted to have two amazing talks in our session. So the first talk of the session is by Jacob Feldman, who is going to tell us about dynamic pricing with menu costs, approximation schemes, and applications to grocery retail. So the talk is going to be between 25 to 30 minutes. If audience have any questions, please write your question in the chat. I'm going to monitor the chat. I'll try to keep the speaker uninterrupted. In case that there's an important clarifying question, I'll try to ask that from the speaker, but I'll do my best to keep the talk uninterrupted. We will have a 5-minute short Q&A at the end. And then the talk is going to be followed by a discussion by Srikanth Jagabathula. I hope I pronounced your last name correctly, Srikanth. I'll do my best. So with that, the floor is yours, Jacob. Looking forward to your talk.
Thanks, Rad. All right. So thanks for tuning in. I'm Jake Feldman at WashU, and this is joint work with Danny Segev at Tel Aviv University. So the motivation for this work and sort of where this work stemmed was from the realization that in something like 99% of dynamic pricing papers or online resource allocation papers with choice, so like network revenue management or single leg revenue management, there's this fundamental assumption that changing prices or changing assortments between periods is free. When there's sort of ample evidence that in a lot of applications, this isn't true. So what we're going to do is we're going to look at sort of a classical dynamic pricing setting, and we're going to inject this notion of menu costs. This idea that when you change prices, you have to pay. And so from a practical perspective, we'll sort of add this new element to bring it closer sort of to the real world and a host of applications. And from a theoretical perspective, with this small twist to sort of a classical dynamic programming framework, dynamic pricing framework, we get sort of this new setting that's pretty difficult. And I hope you sort of believe me when I introduce the problem at a high level, but we also sort of have theoretical evidence that it's difficult as well. So let me jump into sort of just 3 high-level contributions of this talk. So the first is just a modeling one, right? So as I'll sort of try to convince you, menu costs, this idea that changing prices isn't free, is pervasive, it's important, and it really hasn't been studied that much. So here we have a couple of quotes. The first from Chen and Simchi Levy from 2012. They say a predominant assumption made in the existing inventory and pricing literature is that price adjustment is costless. Okay, and the quote goes on to sort of give you this paper here, this Levy et al. 97 paper that looks at estimating and sort of looking at the significance of these menu costs, specifically in a grocery retail setting similar to ours. And as you can see at the end of that quote, right, they find that these menu costs can make up as much as 40% of the reported profits. Okay. Another quote from Nedison, and this quote here sort of shows you why these menu costs arise. So in applications like cruise lines and theaters, right, the sale is made through a network of agents with prices printed in catalogs, which makes price adjustments costly. A similar problem is faced by catalog retailers who incur significant costs each time prices change and new catalogs have to be printed. And the end of that quote sort of says there's also marketing costs sometimes with associated price changes. So this quote also goes on to sort of identify again that there's very little work that sort of relates dynamic pricing and menu costs, right? Yet studies that link the cost of price changes to dynamic pricing policies are scarce. So these are quotes from 2006 and 2012, but we actually sort of dug into recent publications, and we found that of the almost 1,200 studies published in Informs journals between 1980 and 2020 that mentioned dynamic pricing or revenue management, we found only 17 mention menu costs or price adjustment costs, and none of these papers consider a multi-product, multi-period setting. So sort of the most sort of general realistic setting hasn't fully been accounted for explicitly with the notion of menu costs. There are a few papers that do get sort of relatively close, and I'll sort of mention those in a few slides. But none of them explicitly mention menu costs. There's sort of this implicit notion that changing assortments or changing prices isn't free. And also I'll mention sort of I've had independent discussions with Hussein about his work at Amazon, and he sort of mentioned that Amazon cares about this stuff in sort of a different way. They make assortment decisions thinking like, when I move from one period to the next, I don't want to change too many of the products. So I don't want to have like one assortment and then another assortment that's completely different. So they have these constraints that sort of say, when I move from one time period to the next, at least 50% of the products, let's just say, have to stay the same. And so they have sort of a different notion of menu costs, but it's something they're thinking about. Let me just say that. So first contribution is purely modeling, sort of introducing and studying this sort of new idea of menu costs. And the second is obviously sort of what progress do we make on this problem? Okay, and the theory that we present sort of comes in two flavors. The first is 4 distinct hardness results. So what these hardness results essentially do is they say, let's look at the problem. Let's simplify it along any potential dimension. And we can essentially show that when you do that, the problem is still NP hard, no matter sort of how you simplify things. So we use these hardness results to sort of potentially explain, maybe why there's not a lot of work, and also just sort of convince you that the problem is indeed hard. And the second thing about these hardness results, or really sort of one of the hardness results, is that it has important implications for mixed M&L assortment. So mixed M&L assortment is a very well-studied problem, and we present sort of a completely new hardness result that has important implications actually related to some recent work. So when I formalize these results, I'll sort of tell you about all of that. And then the second flavor is an algorithm. So we have an FP-TOS, so we can get within 1 minus epsilon of optimal. We need a few assumptions to do this. And these assumptions, we argue, are sort of apt for grocery retail. So when I present the theorem, I'll tell you about these assumptions, and I'll sort of argue that each of them is relevant to grocery retail. The third contribution is sort of an extremely extensive set of numerical experiments where we compare static versus dynamic pricing policies in a grocery retail setting. So once I tell you what a pricing policy is, I'll tell you what I mean by static and dynamic. But I think you probably have a decent idea of what that means. And to the best of my knowledge, there aren't a tremendous number of papers that provide sort of a rigorous, comprehensive comparison of these two sorts of policies. And what I mean by rigorous and comprehensive is we take a huge data set. So this Nielsen retail scanner data set from Kilt Center for Marketing, billions of transactions. So at various grocery stores, for various products, for various weeks, we know sort of the sales. And we use this data to estimate everything. So we estimate demand, which, as I'll sort of tell you in a second, is going to be M&L based. We estimate marginal costs, and we estimate menu costs. So we estimate the full spectrum, and that gives us this sort of very realistic test suite of instances. And then we use our FP-TOS to compute near optimal static and dynamic pricing. And what we find is actually in this sort of grocery retail setting, dynamic pricing doesn't do a tremendous amount. So the average gains here are about 0.5%. So this was fairly surprising. We sort of had this idea in our mind that dynamic pricing will do a lot better than static pricing, but we're actually not the first to sort of realize that this can happen in a bunch of realistic scenarios. So there are past works that sort of surprisingly say that static can do just as well as dynamic. The first is sort of looking when you have strategic customers, and the second one is rotatable spare parts. So both these papers sort of realize the potential of dynamic pricing, of static pricing, and sort of surprisingly show that it's basically as good as dynamic pricing. So our work sort of fits alongside these. We show, at least our numerical experiments reveal that in this grocery retail setting, there isn't much to gain from dynamic pricing. Now, unfortunately, Nielsen has a policy that you have to submit. You have to submit presentations 30 days in advance. And I didn't have this done 30 days before this talk, so I can't tell you much more about this, even though it's all in the paper, which is available. But if you want to know sort of all the details, we have a comprehensive appendix that sort of explains everything about the data and how we estimate everything. And I'm happy to chat offline about it. Okay, so let me at least formulate the problem. So sort of tell you about the problem, tell you about the hardness, tell you about the FP-TOS, and give you at least a little intuition behind how we derive it. Okay, so we're going to consider a discrete pricing setting. So we have n products, each endowed with a integer starting inventory, and each of these products can be priced at one of L levels, and the L levels can be different for each product. Okay. We'll have T discrete time periods, and the number of arriving customers in each time period will follow an arbitrary discrete distribution. So NT is going to be the random number of customers arriving in period T. So there are some implications about the distribution of NT, but they're sort of technical, and I'm not going to get into that. We can just assume, for example, it's a Poisson. Okay. Demand is going to be M&L based. Okay. So that means for every product I and for every level that we could price it at, and every time period, we have an associated preference weight. Okay, so it's going to be time dependent. We're going to have a time dependent M&L model. And for tractability, we needed to assume static substitution. Okay, so what I mean by static substitution is that customers are always going to choose amongst the n products, even if one is stocked out. And if their most preferred product is not available, they're not going to substitute. They're just going to leave the store. Okay, so that's an assumption we make for tractability, but as I'll argue, it sort of also fits within the grocery retail space. And we're not the first to make this assumption. So multiple papers have sort of thought about this idea of static substitution and generally use it for tractability reasons. This top paper looks at sort of inventory decisions published in OR, and this bottom paper looks at dynamic pricing published in Management Science. Okay, and then the menu cost. So we're going to encode the notion of menu cost, and there's a lot of ways you could encode it. We're going to encode it through a budget. So we're going to assume the retailer has a budget of B to spend on menu costs. There's two kinds of menu costs. A fixed cost of F is incurred anytime you change any price, and then a variable menu cost V is incurred for each price change. Okay, so I'll say that now, and then I'll sort of formalize and formally write down the constraint in a few slides. And then a pricing strategy. So our pricing strategies are going to be time-dependent calendars of prices encoded by this binary vector. Okay, so XILT is just 1 if I price product I at level L in period T and 0 otherwise. So we're going to assume the retailer sort of decides these in advance. So it decides that full binary vector in advance. It's a dynamic policy is one that's going to change over time. So it's going to be time-dependent, but it's not going to respond to inventory depletions. A static one is just one that sets the prices and doesn't change them throughout the time periods. Okay. In both cases, sort of all of our hardness results actually apply to the static problem as well. So static is really just as hard as dynamic in this case. Okay. So just to formalize things a little bit more, we have our arrival process, we have our M&L based demand, and we have our pricing strategy, this calendar of prices. The demand for product I in period T with respect to a fixed pricing strategy X is going to be this. So DIT is going to be the random demand for product I in period T. I compute it by summing up over the number of random arrivals. And then YIT is just going to be an indicator if the customer new is interested in product I in period T. Okay, and it's one with these M&L choice probabilities. So that's what that's saying below there. Okay, so DIT is going to be the random demand, and UIT is going to be the random inventory. Okay, so how do I compute the random inventory? It's very easy through this recursive formula. It's just my initial inventory minus all the demand in previous time periods, and then you take the positive part. Okay, so sort of very natural definition. So DI is random demand, and UI is random inventory. Okay. With those two ingredients, I can write down the expected revenue, but first let me give you the a formal account of the menu cost constraint. So as I mentioned, two kinds of menu costs, right? The first is going to be the variable menu costs. Again, that's just incurred every time I change prices. So that's just V times the number of times I change prices in each period. Let's just assume that delta function just counts that number of times. So that C var there gives me for a fixed pricing strategy X, the total variable menu costs. My total fixed menu cost in this case, right, is just incurred every time I change prices at all. In other words, I look between every period. I just ask, is delta greater than 0? If it is, I change prices. So I pick up that F. So my menu cost constraint just says total fixed plus total variable has to be less than B. Okay, and it's not hard to see that this encodes the constraint that if you just had a limit on the total number of times you can change prices, this constraint would generalize that, right? You just take F to be 0, you take V to be 1, and you take B to be the number of times you're allowed to change prices. And this is precisely a constraint on the total number of times you can change prices. So this generalizes that constraint. Okay, let's put everything together just to give you the formal account of the problem. So what's my revenue for a fixed expected revenue for a fixed pricing strategy X? Well, I sum up over every period. I sum up over every product. My total sales is just the random sales is just the expectation of the inventory and the demand. And then I multiply by the price I charge for that item. So each item can obviously only be priced at one price. So that outer sum there just picks up the price that I is charged at. So that's my expected revenue. And so my goal is to choose these calendars of prices to maximize expected revenue, subject to my menu cost constraint. Okay. Okay, so let me move into the first flavor of results. Oh, before I do that, let me just mention the papers that are sort of closest. Yannis Stamatopoulos at UT Austin has sort of really sort of pioneered really in our field this notion of menu cost. He's written a lot of papers on it. Here are just two. His first one with Achal and Tony look at sort of what happens when a retailer goes from printed price labels to digital, right? So when you have digital labels, it's a lot easier to change prices. So they sort of look at the effect of that in terms of menu costs and sort of dynamic pricing strategies. And the bottom one there with Naveed and Robbie looks at sort of explaining how inventory record inaccuracy and menu costs explain price trajectories in grocery retail. Okay, so these are sort of two works that sort of look outside the scope of choosing optimal prices and sort of the effects of menu costs and things like that. There are three related works that these are probably the related works that are closest. Again, none of them explicitly mention menu costs, but they all do kind of implicitly. This top one only looks at a single product setting. And the bottom two do not have an explicit notion of menu cost. They sort of have constraints on the number of times you can change prices. But they really are looking at the middle one looks at sort of heuristics that perform well, and the bottom one looks at regret. We're going to look at approximation schemes, so it's a slightly different perspective. Okay, so let me tell you about the hardness results. Again, the idea here is that if you take the problem and simplify it along any dimension, the problem is still NP hard. The first set of hardness results, which I'll call our part one, we sort of get for free. Those familiar with this setting might realize that this our dynamic pricing setting subsumes mixed M&L assortment. So all we really have to do is show this pricing setting generalizes mixed M&L assortment, and we can directly exploit those results. And to see that, right, what you do is you take a mixed M&L model and you create a time period for every customer type. You have two price levels that are just offer the product or not offer it. You assume infinite inventory, and you just set your menu cost budget to 0, meaning once you choose an assortment or a set of prices, right, you can't change it. So basically, you're just choosing one assortment to be applied to all the customer types or in each time period. And this is a fairly sort of straightforward observation, but allows us to directly exploit sort of known results for mixed M&L assortment. So first being that the general problem can't be approximated within big O to n to the 1 minus epsilon. And this is even with infinite inventory levels. This result is due to this OR paper by Antoine Venit and Jiawei. And then the other one is that even if you have two periods or two customer types in this case, it's still NP hard. Okay, so if you wanted to say, what if I just consider a very small problem? So two periods, the problem is still NP hard. Okay, in these two periods, you have infinite inventory, but customers can choose according to different models in the two periods. So I'll mention that. So these results, again, we sort of get for free. And this result is due to a POMS paper by Pat, David, Chao Xu, and Hussein. But here's here's two new results. The first one is that even if you have two periods, and even if in these two periods, each customer chooses according to the same MNL model, the problem is NP hard. Okay. We need a stock out to do this, but we can show that, yeah, even this is sort of like the simplest instance. Two periods, in both periods, they choose according to the same MNL model. The problem is NP hard. Our cornerstone result, and this is the one that applies to mixed MNL assortment, is that we can show that our problem is NP hard to approximate within this polylogarithmic factor, even with infinite inventory, and even when there's exactly one customer arrival in each period. So we know exactly how many customers are going to arrive. There's one. We can show that you can't do better than this polylogarithmic factor. So it turns out that this result, if you just look at our reduction, it's not too hard to see that this result also applies to mixed MNL assortment. So this is the first hardness result for mixed MNL assortment, where there's no restrictions on the arrival probabilities between the customer segments. Okay, so here what we're essentially saying is we're looking at mixed MNL assortment where the arrival probability of each customer segment is the same, is uniform. And previous reductions have sort of needed to assume that the ratio can be exponential in, for example, the number of products. But again, here we're looking at sort of a more realistic setting. We can assume all the arrival probabilities are the same, and we can show you can't do better than this polylogarithmic factor. Okay. And this problem of mixed MNL assortment, where everyone has the same arrival type, is not just sort of one that we sort of pull out of thin air. It's one that this paper here actually studies explicitly and exploits to solve this customization problem. So they look at a problem, a mixed MNL assortment, where every customer type has the same arrival probability, and they use that algorithm to solve their problem. So what we show is that intermediate step, you can't do better than log m, this polylogarithmic factor. Okay, so it's actually a problem that's relevant to some recent work. And again, it's sort of the first hardness result for mixed MNL assortment that puts restrictions on the ratio of these arrival probabilities. So those are our hardness results. Let me tell you a little bit about the FPTAS. But first, let me talk about the assumptions we need. So we do need a number of assumptions. So the first, I think two of them are very reasonable. One of them I'll sort of maybe have to do a little more convincing. The first one is a finite menu of potential prices within the same magnitude, right? So in grocery retail, this is pretty reasonable, right? We're used to seeing sort of things priced in 99-cent or 50-cent increments. And we need to assume sort of that within a product, the minimal and maximal price you can charge can't be sort of exponentially dependent, which is, again, a sort of reasonable assumption. And we see evidence of both of these in the Nielsen data. Again, I can't show you those plots, but they're in the paper. The second one, okay, is, and this is sort of the one you might need a little more convincing, is that the time horizon has to be short. So the calendar we're going to choose has to be for a relatively short time horizon. And this is relevant to grocery retail for a multitude of reasons. And this quote here sort of tells you what those reasons are. First of all, I'll sort of summarize this quote for you. You don't necessarily have to read it. First of all, it's hard to predict in grocery retail. It's hard to predict too far into the future. Okay, so you can't set prices too far into the future because predictions of demand can't be very good. That's one thing this quote says. A second thing, which is not related to T equals big O of 1, but is related to our assumption of static substitution in time-dependent policies that don't change for inventory levels, is this idea of inventory record inaccuracy, right? Even if you wanted to develop policies that were dependent on stockouts, it'd be difficult to do so in a lot of settings because there's inventory record inaccuracy. You don't know precise inventory levels, and to do that, you have to do sort of extensive audits, which grocery retailers don't do very often. Okay. So and the third assumption is we just need reasonably sized inventory levels. Okay, so just to compute the expected revenue, for example, it's going to be a function of the starting inventories. So you can't have them be sort of exponentially dependent on problem parameters. So this is, again, sort of something that's reasonable. Okay, so with all that,
so Jake,
yeah.
Sorry, you have 3 to 4 minutes left.
Perfect. So so here's our theorem, right? Here's the FPTAS for any accuracy level epsilon, we can get within 1 minus epsilon in the following runtime. Okay, so let me sort of break down each of the components. This I is just the size of the input. This is going to be the ratio of minimal and maximal prices within a product, right? So it can't be exponential. You can see the exponential dependent on T. That's why we need T to be big O of 1. And this is the largest starting inventory level. So this can't be something like 2 to the n. Okay, it has to be like polynomial in the number of products, for example. Okay, so let me give you the high level intuition here. It's, I think with this problem here, we do make some significant progress, and I think sort of the algorithmic insights are interesting. But I think there's sort of a lot more that could be said. So what we're doing here isn't necessarily sort of tremendously new techniques. I'd say they're non-trivial, but I think there's lots of work to sort of expand and build upon this. So the high level intuition is we basically just want to break any links between products. So essentially, we want to be able to make our pricing decisions product by product. If we can do that, we can write a DP that goes product by product and sort of keep track of the necessary information to make sure things are feasible and to make sure sort of we choose a near optimal policy. So there are two things that link decisions. The first is M&L demand. Okay, so if I price one product, to know the demand, I need to know the prices of every other product. And the second is the menu cost constraint, and namely the fixed cost, right? If I price a product, right, in order to know if I should charge a fixed cost, I need to know the prices of all the other products in that period. So remember, a fixed cost is incurred if I change any price. To know if I changed any price, right, I need to know sort of all the prices. So these two linking factors, and we use sort of this algorithmic idea of guessing to sort of get rid of these. We guess the total weight offered in each period, and we guess the periods in which the fixed cost is incurred. And what we can do is we can take those guesses. Let's say the total weights are W hat, and the fixed cost is gamma star, and we can inject them into an approximate problem. And what this approximate problem essentially does is it replaces the denominator with these guesses, the denominator in the M&L model. So the total weight is replaced with our guesses W hat. We write constraint 3 to make sure that sort of the weight we ultimately choose is close to that guess. And then we say you can only change prices in time periods in gamma star. So that's what the second one says. And we charge the fixed cost up front. That's what constraint 1 says. So you can only change prices in gamma star. We'll charge the fixed cost up front. And now we only have to keep track of variable costs, which can be kept track product by product. So what we do is we show that this approximate problem is close to the original one. Essentially, it says if you can get an FP-TOS for this, you can get an FP-TOS for the original problem. And having now sort of written these constraints and sort of decomposed the problem, we can get our FP-TOS with a sort of relatively straightforward dynamic program that progresses product by product and prices them individually. So you price each product. In doing so, you keep track of your total weight, you keep track of your total variable cost incurred, and so to make sure things are feasible for 1 and 3. And there are some technical nuances to making sure things work out, certainly. But I'm going to sort of skip those for now and talk about them at a high level. Okay. So thanks for tuning in, and I hope sort of this notion of menu cost, which is a very sort of easy to grasp and simple notion, inspires sort of future work to think about how things change when we say, okay, when you change prices or change assortments, it's not free.
Excellent. Thanks for the great talk. Let's thank Jacob again. So there are no questions in the chat, but I actually have a question. So do you know any APX hardness results if the number of time periods is super constant?
If the number of time periods, no, don't know anything. Don't know anything about hardness of approximation when it's constant.
So there might be a case that you can actually extend your FP-TOS to the case when T is super constant.
Yeah, I'm not sure. Yeah.
Do you have any ideas on that? Have you thought about this case? Basically, my question is, how important is assumption number 2?
So assumption number 2 is important just because of the guessing. So when you guess, so we get the exponential dependency. For example, just thinking about guessing that when the fixed cost is incurred. So when you guess, it's 2 to the T, right? So 2 to the T possible periods. So yeah, getting rid of that. I'm not sure. Yeah, I'm not sure how feasible it is to do that. At least in this at least in this con. I mean, that's the like dealing with the fixed menu cost is the big sort of issue, is like how do you make sure you charge that in a correct way.
I see. But at the same time, there is no formal hardness result.
Yeah.
Excellent. All right. Thank you so much. Let's thank the speaker. So with that, we are going to move to Srikanth's discussion. Srikanth, the floor is yours.
Sure. Let me try and share my screen. Okay, can everyone see my screen?
Yes.
Okay, awesome. So first of all, let me thank the organizers for putting together an amazing conference over the last 3 days. I really enjoyed attending it, even though it's in a virtual format. And also thank you for inviting me to be a discussant of this wonderful work by Jacob and Danny. Congratulations on this nice paper. So what I thought I'll do for my discussion is, which I always do, is like do a quick recap and give a sense of like how I view the results and what I think are kind of really interesting before I get into some of the discussion points. And depending on time, maybe like, you know, if the audience has any questions or if Jacob wants to kind of respond to some of the points, it should be fine. So as Jacob just mentioned, right, like, you know, it's like a classical optimal dynamic pricing problem that they're looking at. And one key thing is that, well, you know, there will be potential costs that will be incurred when the prices are changed. And this isn't something that is usually not thought about. And it is assumed that you could be changing prices like infinitely often, or like the number of price changes really doesn't constrain you in any significant way. It's sort of true in online settings, unless you kind of consider some sort of maybe customer experience standpoint that you're kind of having too many price changes. Like I go to the grocery store today, I see like, you know, the price is like $10. I come back tomorrow and it's like $8. I come back day after tomorrow, it's like $12, right? Like, you know, so there is that element also. And especially for like frequently purchased products, people do remember, you know, the price that they paid maybe in the most recent time period. So definitely, I think this is a very, very interesting problem that has received very, very little attention in the literature. And my sense is that definitely it's true in the offline setting, but it's also true in the online setting if you're trying to sort of endogenize those costs, which are usually not accounted for. So Jake and Danny sort of start off with this kind of setting, which is kind of very standard and classical, like, you know, very similar to other settings that have been looked at in the literature. So you have end products, you're given some initial inventory levels. And one assumption that is made here is that there's a finite set of feasible price levels. Now one could think of like a continuous setting. So there are some papers which have looked at more like static pricing in a where the prices can be continuously chosen. But here, like, you know, they're assuming like a finite set of feasible price levels. And the good thing is this sort of kind of makes it closer to an assortment problem, right? As we have seen, there's a discrete planning horizon. And then from modeling standpoint, so one interesting thing here is that the underlying sort of demand model is non-stationary, meaning the MNL weights are changing over time, right? So the question would be basically, again, if you think of a grocery setting, you know, this week, you know, people have a certain attraction value for each of the products. I come back next week and there was slightly different attraction value for each of the products, right? So I'll come back to this particular assumption and like what it means and like, you know, whether it's necessary or not. And finally, they assume like a budget on the cost of price changes. And I highlighted this because this is sort of the new thing, right? And sort of the key sort of outcome or contribution is, given all these constraints, you know, they want to figure out like what is the optimal price schedule, or what they call calendar, meaning today I want to tell you what is the price that you're going to charge for each of the products for each of the time periods going forward. And one of the things that I want to kind of emphasize here is that, which fits sort of an initially, like, you know, I thought it would be done in a slightly different way, is I was thinking of like a DP, right? Like that's what you would think in these settings, wherein, okay, I have a current inventory level. Let's say there is some budget level, and then I'm going to do some sort of a decision for the current period, and there is some sort of a value to go, which is a function of the remaining inventory and the remaining budget, right? And this sort of makes sense, I guess, you know, if I have the ability to monitor inventory constantly, So after, let's say, 1 week or one time period, I update my inventory levels and sort of solve the, or if I'm able to solve the DP, then basically I have the policy corresponding to the DP. So the output of this, in fact, is not a policy like in a DP setting, but rather like a fixed assignment of prices to each of the products in each of the time periods. Just want to kind of emphasize this. And Jake's argument is a very valid one. And this is something we've also faced in different contexts, especially in grocery context, is that that is not a reasonable assumption in offline grocery setting. Even in actually an online grocery setting, we're trying to work with like Instacart and so on. They have the same issue wherein they don't know what the inventory levels are actually, inventory levels actually are in practice, right? So that is something I thought was very interesting. I wanted to highlight that. And then the other key assumption is what Jake called static substitution. So one way to think about this is that, like, there is substitution behavior, right? Like meaning there is going to be cross price elasticity. So the MNL model captures those cross price elasticities, but it does not capture any stockout based substitution, right? So the stockout part is completely ignored, but what it is being captured is the price based substitution in this context. Okay. So given this, like, what are the kind of key findings? Initially, like, I oriented myself to think about this not as a pricing problem, but as an assortment problem. And that kind of really helped me, like, really understand the results. So the one way to think about this, like, is this key special case, which is an assortment optimization problem under a mixed MNL, or what is known as a finite mixture of MNL models. Now you can think of this as assortment problem with the constraint that only one copy of each product is offered at a time. By one copy, I mean, like, for each product, I can create a copy corresponding to each of the prices that corresponds to some MNL weight. In each time period, it's an assortment problem wherein for each product, I have to pick exactly one of the copies. And setting infinite prices like equivalent to not offering the product, right? So the moment you kind of see this, as Jake mentioned, some of the hardness results sort of come out immediately, right? So it is at least as hard as the assortment optimization under the finite mixture of closure or mixed MNO. That's, you can get there for free. What I found interesting was this result, which is it is hard to approximate even when there are uniform arrival rates. So this was sort of not known in the literature, which sort of goes back to say that, well, this problem is very, very hard, even after putting like lots of restrictions on it. The other thing that I found interesting was that as I was reading the paper, the next thing that came to my mind is that, oh, what if the MNL, it's the same MNL model, what if it's a stationary setting and the MNL model is not changing? In this case, when there's finite inventory, they show that it is hard. My mind went, okay, what happens if it's infinite inventory? And then I had to sort of dig up this paper, which is also quite well known. I haven't done the exact reduction, but basically when you have infinite inventory and there are no when there is infinite inventory and I think you have like infinite budget, then you can basically solve this problem, or at least there's like only one MNL model, you can solve this problem efficiently because it reduces to this assortment planning under MNL model with a totally unimodular constraints. Because for MNL model, the optimal pricing problem is known to be solvable when it is a continuous price. But when you have discrete prices, that is also known to be solvable using an LP. And good reminder for us to have. Okay. And then I won't go too much into this detail, the FPTA that Jake has already presented. And there's a second one which he briefly mentioned, but he did not get a chance to go into it because of, I guess, the Nielsen restriction, is that they did a very nice semi-synthetic study using the Nielsen data. And they compared static pricing, optimal pricing with dynamic pricing, and they found that the dynamic pricing provides only modest gains in their particular setting. So a lot of my discussion will be sort of around this, which I at least initially found it puzzling and also interesting. And there are kind of obvious questions that come to mind when thinking about it. Okay, so let me get into the discussion points. So the first question I had when thinking about this was, okay, so even before we get into the dynamic setting, what about the static pricing policy, right? So which can be arrived at using the following special setting, right? Like you assume that the budget is 0, so you set the prices once, and you use the same prices, like for the remaining time period. And then let's assume there's infinite inventory, so you're not worried about like inventory considerations or stock out considerations. So then this reduces to price optimization under a finite mixture of logit models. There is one paper that is very recent that has been published, which proposes like a p-TAS for this particular problem, but they look at the setting where the prices are continuous. It's not a discrete price setting. Okay, and so a natural question is like, how is this kind of algorithm sort of related to this? And their p-TAS also assumes a constant number of mixture components. I didn't see any discussion with respect to this result, but it'll be nice to see if there are any overlap in the proof techniques and how like this result sort of relates to the result you have in your paper. A related thing is that, again, like, in practice, I can start with the static pricing problem, right, which they have a nice FP task for, which is what they implement in the numerics, and then sort of understand, like, how does this compare against what I would do otherwise in the absence of this algorithm, right? So even, as I said, even before getting to dynamic, which is the problem being considered, let's just stick to the static case. And what is my best alternative? The one thing I can think of is you can run an MILP and then kind of see what happens. But to the best of my knowledge, I don't think there are that many papers out there looking at this particular problem. So I think already that is sort of an interesting contribution to start with. Now, the second issue is like trying to understand the source of these like modest improvements that they're observing in this dynamic versus static setting, right? So just taking a step back, right? Like, why do we expect in general, why do we think we need a dynamic pricing policy as opposed to a static pricing policy, right? So usually there are two drivers, and this applies to like, any revenue management setting, right? So I would need a dynamic pricing policy, maybe because I have some inventory, some scarcity, right? Some sort of an inventory constraint. Or I'm in a non-stationary setting, let's say like Uber, right? Like, let's say I have infinite inventory, even then I may want to change my prices because the demand model is changing over time. So the interesting thing is both of these things are happening here. Yet, we are not seeing much of an improvement of dynamic over static. So which leads me to believe, maybe in the simulation, the starting inventory is too high. In the paper, they mentioned that they set, I think, about 90% of like the inventory is available, which is probably true in grocery settings. But maybe there are some product categories where, there are more frequent stockouts, right? So one possibility could be maybe we should focus on categories where there is inventory is not that high. The other question I had, which at least I did not find in the paper, is the MNL model really changing over time? Why do we expect the MNL model to change in the grocery setting from one period to another period? Again, this could vary from one product category to another product category, or they look at week by week. Again, conceptually, if I look at maybe month by month, maybe I'll see kind of more variation, because let's say there's some seasonal products, and if I look at like, during the seasonal period, then I'll see kind of variation in the MNL model. So perhaps, the MNL model itself is not varying that much, or maybe they're like very, very small variations in the MNL model, which is probably what is causing this. The last thing I have is there's this budget constraint, right? I would say, okay, let's try to get rid of the budget constraint and see how much we get, right? So at least we know that how much money we are sort of leaving on the table because of this budget constraint. Again, in practice, like, I could be convinced to invest and incur this cost if I can see the upside in return for that, right? And the last thing is lack of inventory update between periods. So maybe if I'm able to audit and then spend the effort to audit and get the inventory update in each time period, maybe then again, I would be able to get like a lot more, right? So if I had the ability, again, how much money am I leaving on the table? So this analysis could be very, very interesting because it's by default assumed that the dynamic is better than static, but it'll be nice to understand, at least in one popular and important area like grocery retail, what this would look like. One last point, which is more of a minor one, is like going back to the MILP. I was wondering, like, first of all, I should say that like FP tasks, unlike P tasks, is not just theoretical. It can actually be implemented, and it can actually work in practice. So that is one of the amazing things about this. It's an FP task. So they have an implementation of this, and how does this compare against a standard like or natural MILP formulation of the problem, which one can obtain in this case. Okay. So anyway, so these were like high level what I was thinking about it, or thoughts that kind of came to my mind as I was reading the paper and I was thinking about the proposed results in this paper. So let me stop here.
Awesome. Thank you so much, Srikanth, for the intriguing discussion. Thanks again to Jake and Danny for the great paper and also the great talk. So in the interest of time, let's actually move to the second talk of the session. So we are going to have Yifeng Teng as our speaker, who is going to tell us about his work on pricing query complexity of revenue maximization, which is a joint work with Renato, Paes, Leme, Balasubramanian, and Pratik, Worah. So the talk is going to be followed by a discussion by Yonatan Gur. So with that, Yifeng, the floor is yours.
Yeah. So can I see you sharing?
Yes, we can.
Yeah, great. Yeah. So hello everyone. This is Yifeng Teng from Google Research, and I'm honored to be here. Today I'm going to talk about the pricing query complexity of revenue maximization, and this is joint work with Renato plus Leme, Balasubramanian, and Pratik. In this talk, we are mostly studying, but not limited to, the revenue maximization problem. And the revenue maximization is the most common objective of the seller in an auction, which aims to maximize the total payment collected from the buyers. And the revenue maximization problem has been particularly interesting as the online advertising and digital marketplaces have been important in daily life. And literature in this area has been usually assuming that the buyer's value distributions are publicly known to the seller in the evaluation settings, and the seller designs the revenue maximizing mechanism and does the optimization using the distribution of information. So, for example, consider a problem where a seller wants to sell a single item to a buyer with values drawn from a fixed distribution. What's the optimal mechanism for this problem? The optimal mechanism design theory shows that whether the seller is allowed to have like an arbitrarily complicated mechanism, the revenue maximizing mechanism is still to post a single multiplier reserve price, and the buyer purchases the item if she realizes the value is at least the reserve price. So such a single buyer mechanism design problem is not just for theoretical interest, but is also practical, as for example, in the online advertising setting. It is kind of normal that for some kind of query, there's no competition at all, so the multi-buyer auction actually degenerates to a single buyer set. One problem about the Bayesian model mentioned in the first page is that the assumption on the seller having access to the complete prior information of the buyers can be unreasonable. So one possible approach to solve the problem is to assume that the seller can have access to sample of buyers via historical market data. So for example, consider an ad platform running a second price auction with a reserve. And since the second price auction is truthful, it means that the bid of each bidder equals to her true value. And the seller can collect the samples of the bidders' value distributions and via the bidder's bids. And then the seller can optimize the reserve prices over a collected data set. One important question to ask in this particular sample setting is the following. So for an unknown distribution, how many samples are needed to determine a parameter of interest, such as the optimal multiplier reserve price for a single buyer problem? So there have been a long line of work in the past decade on the revenue maximization problem, both in the single parameter setting, where the seller has one item to sell, and in the multi-parameter setting, where the seller sells multiple items. So the sample access model is more realistic than the full information setting, but still have some kind of limitations. So specifically, the samples from the bidder's value distributions are not always available. So again, we take an online advertising market as an example. So for the first price auction run by like major display advertising providers and the generalized second price auction run by, for example, Google search ads. So they are kind of very popular auctions, but are not truthful. So for those not truthful auctions, a bid may be computed by some kind of complicated bidding algorithm behind the advertisers. So the bids actually cannot be viewed as the samples of the bidder's value. However, so from those non-truthful mechanisms, so the seller can still at least observe whether the bidder's value is above the reserve price. So now we introduce the model I want to discuss today, that is the pricing query complexity model. So specifically for a known distribution, we want to ask that how many pricing queries are needed to determine the parameter of interest. So note that compared to the sample complexity model, so the major difference is that we replace the samples by the pricing queries here. So a pricing query is defined as follows. So firstly, we'll draw a value from the distribution of the buyer. And then the seller can choose to post a price P and then observe a binary signal on whether the buyer's value is at least P or not. So in other words, so the seller can get to know whether the buyer can afford to purchase the item at the proposed price or not, but the seller cannot directly get access to the exact sample value. So this can be viewed as a more practical model in those non-truthful mechanisms. So to study the pricing query complexity, we need to first specify like the class of distribution that we want to learn from. So they can be bounded distributions or like a regular distribution or Gaussian distribution and so on. And you can set some restrictions such that the Gaussian distribution is bounded between 0 and 2 or so. So then we want to specify the parameter of interest theta. So it can be some standard distributional parameters such as like median, mean, or variance of the distribution. It can also be viewed as a parameter that we want to optimize in the mechanism design problem. For example, the revenue maximizing monopoly price. It can also be even the cumulative density function that gives the entire picture of the distribution. And finally, we need to determine the loss function for the estimated parameters. So for different parameters we learn, we have different metrics. For example, when learning the mean of the distribution, the loss function can be the L1 loss between the estimated mean and the true mean. So like it can also be some other loss. I'm just saying an example. When learning the median of the distribution, the loss function can be the quantile difference, indicating that what's the difference between the quantile of the estimated median and the quantile of the true median, which is exactly 1/2. When learning the optimal monopoly reserve price, the loss function can be the corresponding revenue difference, between the estimated monopoly price and the optimal price. When learning the entire distribution, it can be some distance function between two distributions, such as like the total variation distance or like chromograph distance or level distance. We can summarize our model as follows. So for the sample complexity problem, the typical question asked is that for an unknown distribution from a fixed distribution class, given ID samples from the distribution, we want to compute an estimated parameter such that the distance from the true parameter is minimized. And how many samples are needed such that the estimated parameter differs from the true parameter by a small epsilon with probability at least 1 or 1 minus delta. So here delta can be some small constant, for example, 1 or 3 or like 100 or some even smaller constants. In this work, we asked similar questions for the pricing curious. So for an unknown distribution from a fixed distribution class, given ID samples of the distribution unknown to the seller adaptively posts price in each round and observe the binary signals indicating whether price at each round is smaller than the value sample in that round or not. And again, we asked a question about like how many adaptive samples and how many samples and adaptive curious are needed such that the estimated parameter is close enough to the actual parameter. So we may observe that for any class of distribution, so the pricing curious complexity for the estimating the same parameter with the same accuracy is going to be at least the value of the sample complexity for estimating the same parameter. So because the value curious actually provide more information than the pricing curious. In this work, we analyzed the pricing curious complexity of various parameters for a variety of distribution classes. The results are summarized in the table shown here, and we may notice that for some specific cases, such that learning the mean of a normal distribution, so like with the mean bounded between 0 and 1, the pricing curious complexity and the sample complexity are exactly the same. And for some problems like learning the monopoly prices of regular distributions, so the pricing curious complexity and the sample complexity are close up to a polylog 1 or epsilon factor. And for problems like learning the distributions entirely for some special distributions or general distributions, or like learning the monopoly prices for MHR distributions, there is a strict gap between the pricing curious complexity and the sample complexity due to the information loss. So here I would like to show some of the results in the table. I will show by estimating the median of distribution, or more specifically, the mean of a Gaussian distribution as a warm-up, and then extend the proof to find the monopoly price for a regular distribution, and finally discuss briefly how to prove a lower bound results. So let's start with estimating the median of this distribution. So for distribution with median between 0 and 1, so how many curious are needed to estimate the median such that the corresponding quantile of the estimated median is within epsilon from half. So the sample complexity is exactly 1 over epsilon squared by using the empirical median. And we show that how we can use like the same number of pricing curious up to a polylog factor to find a good estimate of the median. So the idea is that the following observation. So we are going to use binary search and some kind of idea of the confidence interval from the algorithm like UCB, plus the observation that for any price P, if we repeatedly price at the same price for K rounds, then we can get an estimate of the quantile of P in the distribution within a additive error of 1 over square root K. So this happens with high probability. So thus, like to view the confidence interval of length 1 over square root K, we can have we can use the K samples to have this confidence interval that contains the true value of FP. So building on this observation, we can have the following binary search algorithm. So basically, we just maintain a range of possible medians setting to be 0, 1 at the beginning, and then we repeatedly post the prices at P star being the middle point of the interval. So once once 1/2 falls out of the confidence interval of FP star, so the algorithm is going to update the candidate interval to either the left half or the right half of the original interval, depending on whether the quantile of the P star is below 1/2 or greater than 1/2 from what we learned. So if the cumulative density function is smooth around median, then like log 1 or epsilon binary search steps are enough to locate the price with a quantile close to 1/2. So it can also be viewed as a streaming algorithm that at any time n, so the price returns is going to have a estimated, so like the quantile is about 1/2 plus 1 over k, 1 square root k from the median. So a special case of the estimation is to estimate like the mean or median of the Gaussian distribution. So what's the exact pricing Fourier complexity for this problem? So the sample complexity for estimating the mean is actually like the variance over sigma square by using the empirical median. And we can show that actually we can use exactly the same pricing Fourier complexity to find the empirical, so to find a good median. So if we directly apply the Paes algorithm for finding the median of the general distributions, we are going to lose a polylog factor. And the observation is that if we want to optimize this, we can. So since Gaussian distribution is actually a parametric family, like with a single parameter or like with 2 parameters, but here we have fixed the sigma. We can directly calculate a good median from the quantile of a specific price instead of doing the full binary search. So to be more precise, we can use the Paes algorithm to find the price P such that the corresponding quantile is bounded away from 0 to 1. And then we can use the sigma square over epsilon square steps to give a good estimate of the quantile of P. And finally, we can reverse engineer the estimated mean from the estimated quantile, and such an estimated mean solving from the equation is actually good enough. So now we show how similar ideas can be used to estimate the optimal molecular price for the regular distributions. In particular, what is the number of curates needed to estimate the molecular price such that the corresponding revenue is epsilon away from the optimum pricing? So you can see that actually for the single item problem, the revenue of a fixed price theta is calculated by theta times 1 minus f theta, because like 1 minus f theta is the probability of acceptance of the item. The class of regular distributions is defined by those with concave revenue curve in the quantile space. So it contains some important distributions like the uniform distribution or exponential or normal distributions. The sample complexity for getting the approximately good molecular price is 1 over epsilon square by just calculating the optimal molecular price of the empirical distribution. So we show that for the pricing Fourier complexity, we can also do the same number of pricing curates via a more careful binary search process. There are some important properties of a regular distribution. So firstly, the revenue function of a regular distribution is single peaked. So it means that there can only be a single point or a single interval that have the highest revenue. And the second property of the regular distribution is something we call the relatively flatness. This means that due to the concavity of the revenue curve in the quantile space, so although the revenue curve in the value space is not guaranteed to be concave, it can also not hide a high revenue point when measured with respect to 4 points of equal distance. You can see from the figure what does it mean. So if 4 prices P1 to P4 with equal distances have approximately the same revenue, and for any price between P1 and P4, they all have roughly the same revenue. So the only constraint we have is that P4 should be some constant times P1, so which means that P1 is not very close to 0. So this figure is actually a case that cannot happen. So if the 4 points have almost the same revenue, then any price between P1, P2, and P3 should not lead to a high revenue. And such a relative flatness property can provide a nice sloping condition for the binary search algorithm for the molecular price. So now we state the algorithm for finding the good molecular price. So the algorithm is based on the first building block that we mentioned, that repeatedly price at any price for 1 over epsilon square steps can give an estimate of the quantile of the price with the additive epsilon error. So it can also give an estimate of the revenue with epsilon error. So given this, we can perform the search algorithm as follows. The algorithm always maintains a list of candidate intervals that contain the optimal molecular price, starting from interval only 0, 1 in the list. And at each step, we are going to pick a candidate interval from the list and estimate the revenue at 5 equal distant points between L and R. And then we can discuss what happens based on the estimated revenue. I can quickly skim those cases. So the one sloping case is that what happens when the length of the interval is small. So pricing at L is going to be approximately the best in the interval because almost all the points have the same revenue. And if all of the revenue at all of the points are estimated to be similar, so it's from the relatively flattened lemma, we can only we can put interval LP1 back and remove all of the other intervals since the price in P1R has almost the same revenue as P1. And when the estimated revenue of L is much smaller, or the estimated revenue of R is much smaller, we can put back, for example, 2 intervals LP3 and P3R back to L. So notice that the revenue curve is decreasing between P3 and R. So it means that although the optimal price may be between P3 and R, it cannot fall on the right side of R. So we can remove the all intervals from the list on the right side of R. And similarly, in the case where the price at L and R have low revenue, we can remove all of the intervals on the left or on the right of on the left of L or on the right of R. If the left 2 points are having smaller estimated revenue than the rest, we can actually add P1R back to the list and remove every interval on the left of L, since they cannot include the best molecular price because the revenue curve is single peaked. And this happens to the same case where the right 2 points are having smaller estimated revenue. So basically, we have actually exhaustively counted all of the cases, and we can show the algorithm terminus quickly by the following observations. So the first observation is that if the algorithm always select the second leftmost interval from list. When there are multiple intervals available, then the candidate list actually always contain at most 3 intervals at the same time. So this means like the searching cost of each step is actually very small. So the second observation is that after each iteration, like either one of the interval of length d splits to multiple intervals of length at most 3/4 of the original interval, or with some other intervals getting removed, or like one of the interval of length d shrink to the new interval of length at most 3/4. So basically, combining these two observations, the first observation is saying that the number of candidate intervals does not explode, and the second observation is saying that it's like the length of the largest interval is actually shrinking. So plus some further analysis, we can show that the search algorithm actually terminates in log 1 or epsilon rounds. So
so Yifeng, you have between 3 to 4 minutes left.
Okay, sure. Yeah. So so we have shown upper bound of estimating the molecular reserve price for regular distributions. So what about the lower bounds? Like how many samples are needed when we want to learn a good molecular price for a regular distribution? So actually, to complement the upper bound results, we provide a matching lower bound for more restricted class of distribution. And we show that for the class of all monotone hazard rate distributions on 0, 1, 1 over epsilon square pricing theories are actually required to learn a good molecular price such that the random loss is small. So the MHR distribution is a subset of regular distributions. So it means that for the regular distribution, like the 1 over epsilon square pricing theory complexity is actually tight up to logarithmic factor. So we know that so by Huang et al., the sample complexity for estimating the molecular price for MHR distribution is actually 1 over epsilon to the 1.5. So this is strictly less than the pricing theory complexity. And it shows an example of the strict separation between two concepts. So we briefly discussed how the lower bound result can be proved. And actually, the key observation is that for any two distributions that are close, they are hard to distinguish. So in particular, if two distributions are different in the sense that for every value, both FB and 1 minus FB are multiplicatively close for two distributions, then 1 over epsilon square pricing theory complexity are needed to distinguish the two distributions. Then we are able to construct two MHR distributions satisfying the property that both the above property in the lemma are satisfied, and also no price can get epsilon close to the optimal revenue for both distributions at the same time. So this leads to the omega 1 over epsilon square pricing theory complexity lower bound. Now I would like to conclude my talk. So we propose an alternative model of the sample complexity. So the pricing theory complexity, where the seller only has access to the Boolean signals from pricing, and then we extend the results on the sample complexity for learning important parameters for the revenue maximization problem. For example, the molecular reserve price to the pricing theory complexity model. And in the future, we can extend more results from the sample complexity literature to the pricing theory complexity. And that's all. Thank you.
Thank you so much, Yifeng, for the great talk. Let's thank the speaker again. So we have time for 1 or 2 questions. There were no questions in the chat. If no one has any questions, I would like to ask 1 question. All right, let me shoot my question. So Yifeng, as you were explaining, I was thinking about the connection between sample complexity and the regret bound in the adversarial online learning version of the problem when you post prices. So basically, sample complexity lower bounds will give you lower bounds on the regret of online learning algorithm for dynamic pricing in the digital goods setting. Have you thought about any such connection when you think about pricing query complexity? Like,
I feel like I haven't thought about the problem, but so the sample complexity is actually very powerful, but the pricing query complexity is actually kind of a special case of online learning. So it should only lead to the lower bounds on a very special case of the online learning algorithms, like maybe those with only access to the binary signals. But I'm not certain about that. So definitely, this is an interesting question to discuss.
I guess the more interesting question is, can you basically match the sample complexity lower bounds in the adversarial online learning version through a regret bound? And I'm curious to see if any such result is possible, because it is possible for the pricing problem. You can maybe chat about it, that's fine.
Yeah, sure.
All right, excellent. So in the interest of time, let's actually switch to our discussion. So we are very happy to have Yoni to discuss the paper for us. With that, the floor is yours, Yoni.
Thank you very much, Rad. Let me share my screen. All right, so thank you very much for inviting me to discuss this paper. And thank you, Yifeng, for the interesting presentation. So the motivation of the paper that Yifeng just presented lies in a setting with pricing with a known demand, where it is often not simple to obtain unbiased observations of consumers' willingness to pay or values, but in many online settings, one may obtain access to data that is consisting of spot prices and consumers' reaction to that spot prices in terms of purchasing decisions. So indications of whether or not the value is higher or lower than the price. The main motivating example is the one of online ad auctions with announced reserve price. Oftentimes, for example, with budgeted campaigns, first price auctions, general second price auctions, and so forth, bids are not unbiased observations from the value distribution, but they truthfully reveal whether or not the valuation is higher than the reserve price. With that in mind, the paper considers at a high level a very fundamental question: how many price queries are required in order to generate certain revenue? I want to mention that Yifeng described various objectives like the median, the CDF, and so forth. I will focus mainly on the fraction of the revenue that can be recovered out of the optimal revenue, or the ability to approximate the monopoly price, basically, which is perhaps the one of that is most interesting, at least for me. And then how to generate good price queries or good data sets that lead us there. More precisely, the question that the paper asks, the question of what is the fastest achievable rate at which estimates can be guaranteed to approach the optimal revenue asymptotically as the size of the data grows large, and this quantity, referred to as price query complexity, is then contrasted with the sample complexity, where data is consisting of realizations from the value distribution. In terms of analysis, by providing lower and upper bounds, the paper characterized the minimax pricing queries complexity in the asymptotic regime associated with approximating important characteristics, including the monopoly price, and few classes of distribution. This is the table that also Yifeng showed you earlier. And then compare that with the minimax sample complexity, where data is consisting of IID observations for a distribution D. Overall, I enjoyed reading the paper very much. I think it's a very good paper. So I would like to congratulate the authors for their work. I think the paper is very well motivated. And the analysis is quite complete in terms of providing matching lower and upper bounds on a variety of characteristics and distributions. This discussion will focus on my view or my overview of the results and how they complement other papers in the revenue management and pricing literature along three different perspectives. One is the data structure perspective. Two is the policy design question. And three is the problem formulation. So to start with the data structure, the paper focuses actually on contrasting results that are established here with the equivalent results from the sample complexity problem, where data consists of IID observations from the value distribution. In that setting, the samples data setting, the main paper results, asymptotic results are contrasted with is that of Wang, Mansour, and Rafgarden, and that look at various aspects of the problem, but among other things, characterize the rate at which one can approach the optimal revenue when the data set is large. On the other hand, there are other papers that didn't look at the asymptotic regime when we have ample data, but actually on the other extreme, when there is only very little data, one or two observations, and ask what the very much related question of what fraction of the optimal revenue can one guarantee based on the data set of IID samples from the demand distribution. So when we have a lot of data, we can approach 100% of the optimal revenue. The question becomes, at what rate can we approach 100% of the revenue? With little data, the first order question is what fraction of the optimal revenue can we actually recover? And there are various papers that study that question from both impossibility perspective and lower bounds, and also upper bounds and optimal pricing policies under limited data. So that's roughly the picture along the for the samples data structure. Now turning to the price queries data, what we have here is on the right side is basically the present paper that asks what considering data set of price queries. What is the rate at which one can approach the optimal revenue when the data set is large? And in this sense, the comparison to Wang et al. Is very sensible. But also, considering data of price queries, there are papers that are very relevant that considered limited. First, there are also papers that consider no data at all and ask what type of fraction from the optimal revenue can be guaranteed. The papers here on the left-hand side that consider limited data and ask what fraction of the optimal revenue can be recovered. The first paper, Simchi-Levi, asks more about constructing the demand function, which is clearly a related question. The second paper, Alua, Bahamu, and Besbes, a very relevant paper that considers data that is generated from a static price that does not change. So it can be a lot of data, but it's all generated from a static price, and asks how much of the, what is the fraction of the optimal revenue that can be guaranteed, can be recovered based on that limited data set. So both data structures are very different, obviously, but still there are themes that overarch both data structure of queries and samples. And these are these two main themes. First of all, even limited data can be useful to approximate the optimal revenue. And the second theme is that analysis with little data often gives us indication of the constant that are hidden under the big O in the asymptotic regime. And I think that an exciting research question in either of the regime would be to try and unify the limited and ample data regime to understand how they connect to each other, what is the transition from little data to the asymptotic regime, to further shed light on these two themes. What hides under the big O, and how much can we actually do in the finite data set regime, which is of great interest, clearly. The second point of discussion is the focus of the policy design question. Essentially, when we think about pricing under uncertainty, there are two components to the problem. One is the data set, and one question is how to generate a good data set. The other question is how to price optimally based on the data set that we have. And it's interesting to think about what is the more interesting question in different regimes and under different structures. With sampled data, the more interesting question is the question of pricing given the data. The data is just IID observations from the value distribution. There's not much to say there, and the focus is really on making the best pricing decision based on the data. With the price query data, including the present paper, there is more potentially two interests. Both of the questions can be interesting. With limited data, the focus has been on the pricing decision. So what do we do based, again, on the data that we have? The present paper actually focused on the question of how to endogenously and dynamically generate a good data set, and not on the pricing decision itself. And that makes sense because essentially if we are approximating the monopoly price, we can price using the monopoly price. Now the question becomes, how can we approximate, dynamically generate a data that helps us to approximate the monopoly price in the most efficient way? And in that sense as well, the paper nicely complements what other papers have been looking at in the RMP literature. Finally, the last perspective, as we mentioned, the present paper basically decouples the question of generating the data set and making the pricing decision, and particularly the agent doesn't explicitly optimize performance during the data generation period. We want this period to be as short as we want, so implicitly we care about performance in the first period, but we don't explicitly impose or require any performance guarantees along that data generation period. And the question is basically, can we do that? What if we do care about performance during the data generation period as well? What can we do? So a common approach that is an alternative to this decoupled problem formulation is one that integrates the generation of data and the price optimization dynamically through sequential optimization. This is the literature about exploration and exploitation trade-off, or the learning and earning trade-off. They try to understand how to characterize these trade-offs and how these trade-offs basically balance the generation of useful information and optimization along the path, and basically integrated data generation question and the price optimization question together. And naturally, a sensible approach that has been followed by various studies, various papers in our community. And the question, again, comparing with the present paper, is what are the advantages or disadvantages, whether in the pricing region stage or the data generation stage, relative in one approach relative to the other approach, and how policy design is affected by the different objectives. And that's a very, I think, relevant question to the paper, because of the already use of UCB style policies and so forth. A nice analogy for that type of questions is given by the literature on best arm identification in the multi-arm bandit literature. There, the action set is discrete rather than convex, like here. And still, there is the traditional multi-arm bandit literature that considers sequential optimization that combines data generation and optimization along the path. And there is the literature on best arm identification that focuses on the question of getting a good approximate of the best arm. And questions like how policies are different and what is the advantage in different periods are actually questions that are followed up and are considered in that literature stream. And with that, I would like to conclude to congratulate again Yifeng and the co-authors for the nice paper, and to thank the committee, Rad, Ozan, and René for inviting me to discuss the paper. Thank you very much.
Thank you so much for the great discussion, Yoni. So if I may add one thing to the last discussion point that Yoni said, which is kind of related to the question I asked earlier. So if you think about the extension of the sample complexity problem, when the data points are arriving essentially over time, then you can think about pricing as an instance of multi-arm bandit problem when you have one arm for each price, right? And then the sample complexity lower bound will essentially give you a lower bound on the regret of any algorithm under full information. And then when you think about the pricing query complexity, I guess any information theoretic lower bound on the pricing query complexity will give you a lower bound on the regret bound under bandit information. When you only get a binary feedback, you post a price, you only get to see whether the price gets accepted or not really observing the value of the arriving buyer. And I guess studying whether you can match the sample complexity or pricing query complexity lower bound with regret upper bound under the corresponding feedback would be an interesting question. You can even forget about the IID assumption, assume the sequence of values are arising in an adversarial fashion. Whether you can match the regret upper bound with the sample complexity or the query pricing complexity lower bound, I think is an interesting question. All right, thanks everyone for the great talks and the great discussion. And yeah, with that, let's conclude the session. See you around in the remaining part of the conference.
Thank you, Rad.
Thanks, Yoni.